In this video, we're going to talk about the central limit theorem for proportions. So, with a sample proportion, what we're talking about is p hat. This is sample proportion, and that's just our x divided by our total number. Whatever our value is divided by our total number. It's a probability type thing. And so, p is going to be our population proportion, and p hat will be our sample proportion. And when we're talking about these, our mean for proportions is going to be the mean of p hat, which is literally just going to be our population proportion. Okay? And then our standard deviation for proportions, which is sigma sub p hat, is going to be, let me write that equal sign a little bit better, is going to be p times 1 minus p, because remember, proportions, or even probabilities, have to add up to 1, so the opposite of the proportion, divided by the sample size. And remember, since we're talking about standard deviation, we've got to take the square root of it. Okay? So let's look at an example of how to find the mean and standard deviation. So the National Center for Educational Statistics reported that 75% of freshmen entering public high schools in the United States in 2007 graduated with their class in 2011. So that means that 75% actually graduated on time, the other 25% did not. A random sample of 135 freshmen is chosen. So here is our proportion. So p is going to be 0.75, and our n is going to be 135. And we want to find the mean, which the mean for proportions is literally just the proportion itself. So the mean of this is just going to be 0.75. The standard deviation for proportions is going to be p times 1 minus p divided by n, and we take the square root of that. So in this case, we're going to have 1.75, and then 1 minus that, which is 0.25. Our n, which is our number that we're looking at, is going to be 135, and we take the square root of that. And now then I'm going to write down the numbers, how I would multiply and divide them out. This way you can see if you're doing it correctly. I would take 1.75 times 0.75 times 0.25 first, and I would get a 0.1875 divided by 135. And then I would actually do that division next, and I get 0.00138889, and then I would take the square root of that. So that gives me 0.0373 as my standard deviation. It gives me 0.03726678. We'll just round it to 4 decimal places for right now. Okay? So now, let's look at what the central limit theorem says. Remember, the central limit theorem is talking about large numbers, or even if we can do some of these things. So if p hat is the sample proportion for sample size n, what we have to do is we have to think about, is the sample times the proportion greater than or equal to 10? And also, is the opposite true? Is the sample times 1 minus the proportion greater than or equal to 10? If that is the case, we have a large enough sample to assume that it is normally distributed. If it's not normally distributed, we can't use these items as the mean and the standard deviation. That's the whole thing about the central limit theorem, is as long as we have a large enough sample, and that's what this is saying, is if n times p is greater than or equal to 10, and n times 1 minus p greater than or equal to 10, we can use this and assume that it's normally distributed. Okay? So looking at this example, high blood pressure has been identified as a risk factor for heart attacks and strokes. The National Health and Nutrition Examination Survey reported that the proportion of U.S. adults with high blood pressure is 0.3. A sample of 38 U.S. adults is chosen. So we have N being 38, and our P is 0.3. Is it appropriate to use the normal approximation to find the probability? And explain. So what it's wanting us to do is use that central limit theorem. So we want to do N times P and N times 1 minus P. So N times P is going to be 38 times 0.3. So 38 times 0.3 is 11.4, which that's greater than or equal to 10, so that's okay. Now over here, this is going to be 38. 1 minus P is going to be 1 minus 0.3, so that's going to be 0.7. 38 times 0.7 is going to be 26.6. Well, that's still greater than or equal to 10, so we're okay. So it is appropriate to use the normal approximation to find the probability, since both N times P and N times 1 minus P are greater than 10. That's what this question is asking, is can we do it if both of these are greater than or equal to 10? Yes. If not, it's not appropriate to use this. Looking at this same example where our P is equal to 0.3 and our N is equal to 38, we want to find the probability that more than 40% of the people in the sample have high blood pressure. Well, in order to do that, we need to find our mean and our standard deviation. Okay? Well, our mean, that's okay. That is P. So our mean for P hat is 0.3. Well, our standard deviation, remember, is P times 1 minus P divided by N, and we take the square root. So we're going to have 0.3 times 0.7, because that's 1 minus P, divided by 38, and we're going to take the square root. So 0.3 times 0.7 is 0.21 divided by 38. We divide those out, and that gives me 0.005526. I'm going to take the square root of that, and that gives me 0.074339. That's my standard deviation. I had to have those items before I could do this because I'm looking for my z-score. And my z, if you recall, is normally, let's go back to my, okay, so normally it is my z is equal to my x minus my mean divided by my standard deviation. Well, instead of x here, I'm going to be working with p hat, and I have my mean as my mean and my probability, and my standard deviation as my probability. So my proportion that I'm wanting to compare to is 40%. So that's a 0.4. minus the mean of this problem, which is 0.3, and my standard deviation that we just calculated is this, which is 0.074339. So I get 0.1 divided by 0.074339. I need to scroll down. So my z is equal to 1.35. I'm going to scroll back up because I want find the probability that more than 40%. So here's my normal curve. Here's 0.3 or 30%. Here's 40%. And I want more than. Well, remember, if I look up my z, it's going to be here. So I'm going to have to take 1 minus that value. So I'm looking up 1.35. 1.35 is 0.9115. So that's going to be 0.9115 over here. And I'm going to take 1 minus that, which is going to equal to 0.0885. So the probability that more than 40% of the people in the sample have high blood pressure is 0.0885. Now, working with proportions, the main difference in that is having to first find your mean and your standard deviation. It was the same way whenever we had the binomials. You had to find your mean and your standard deviation with it as well. So you'll have to find the mean and the standard deviation for your proportions, and then you'll plug it into your z-score just like you do with everything else. And then if it's to the right, you do 1 minus. If it's to the left, that is your answer. So try some practice problems with proportions and let me know if you have questions.